So, we meet once again. Greetings to you. And yesterday I had started explaining the quantitative analysis by spectrophotometry. We had completed our analysis, our studies on instrumentation, and then I had discussed with you about how we are going to develop a quantitative analysis method by spectrophotometry. I had shown you this technique, this slide also, quantitative analysis by spectrophotometry, and how we develop a color system using different organic reagents or inorganic reagents, etc. And then I had explained to you the typical method development procedure, that is to determine the lambda max and then to determine the other experimental variables for the optimum color development of the reaction. So, these things included pH, reagent concentration, and temperature, stability of the colored product, and effect of high electrolyte concentrations, stoichiometry of the complex, etc. That is a typical method development. And then we had discussed about the preparation, how to prepare a calibration curve, evaluation of interfering substances, matrix effect, and other things. This I had already explained to you earlier. And sometimes it is important to determine the molar absorptivity or Sandel sensitivity, that is and statistical evaluation of the bias. And then applications in diverse matrix also is important, because spectrophotometry is basically a matrix dependent technique. So, any change in the matrix will always lead to slight differences in the absorbances, and then the calibration curve may go a little haywire here and there. Therefore, it is important to test the method every time we have a change in the matrix. So, this slide also I had shown you, and then we are discussing about the simultaneous spectrophotometric analysis. So, here what I said, the if there is only one component to be determined in a given analysis, we do not have a problem, because we can develop a method or use a developed method based on the previous slides. But suppose there are two substances which will react with the same reagent, because basically spectrophotometry is the science of measurement of color. So, if there are two substances which give colored complexes, then the absorbance will become additive. So, I was assuming that, let us assume that there is a analyte A which reacts with a reagent to give you a complex AR and with a lambda max, with a specific lambda max. And suppose I have another component B, and then it reacts with the same reagent R to give you a complex BR, and this may be these two colors are different, but if both of them are present in the same system, then we will be seeing both the colors. Now, if you represent their absorbances in a given system, that is absorbance versus concentration, the complex of AR may be having a lambda max like this, because a spectrum like this, and complex of BR, this is for AR, okay. And a complex BR may have a peak something like this. This is BR. So, any measurement of the sample containing both AR and BR would be the sum of this as well as the other one. The absorbance of this plus this. So, the actual absorbance curve may look something like this and go like this when both AR and BR are present. This is for the lambda max of AR. Same thing is true with respect to lambda max of BR. If this is at lambda 1, this is at lambda 2. If I measure absorbance, this is at lambda 1. This is at lambda 1. Now, the similar thing will happen and I get a curve something like this, and this one will be at lambda 2. So, any measurement either at lambda 1 or lambda 2 would be the sum of the absorbances would be the sum of absorbances of AR and BR. This is the problem. You may be making measurements, but you will be measuring the sum of the absorbances of both AR and BR at any wavelength. Now, the question is, can we sort out this problem and determine both AR and BR? Otherwise, what you have to do is remove B from the matrix by some other means like solvent extraction, precipitation, filtration and things like that. Have AR, determine A and similarly make a procedure for removing the B, removing the A and make the determination of BR. Then you can have the analysis, but we can make use of a little mathematics here, and that is by using the simultaneous determination. So, in simultaneous spectrophotometric analysis, what we do is we recognize that there are two dissimilar chromophores having different lambda max, and if they are different, having different lambda max and different colors, then the molar extinction coefficient also will be different. So, we set up two equations, that is at lambda 1 C1 E1 plus C2 E2 would be the sum of A at absorbance at A lambda 1, C1 epsilon 2, actually it should be epsilon 1, there is an error, and C2 epsilon 2 C1 epsilon 2 at lambda 2 would be A lambda 2. So, the equations are solved for C1 and C2. So, if we know we have C1 and C2 as two unknown concentrations, and absorbance we have two equations and two unknowns we should be able to sort out the concentrations using the a little bit of algebra. So, theoretically if the given matrix contains more than two substances which will give AR, BR and CR, then can I set up a three equation system where a similar thing can be charted out, and then I can determine three unknowns also. Like this, theoretically any number of things can be done, but there is a practical problem with this approach. What is the practical approach? The absorbance lambda max of the two substances should be separated by at least 30 nanometers if I have to apply this method to a fair degree of accuracy. So, this is what I was telling you. Normally 3 component systems people do and people have tried, but more than 3 becomes a little trickier. Then it may not be worth the time and effort and money to do such as an analysis. Okay. So, now we go to another aspect of how to determine the substances at very high or very low concentrations. This also I had explained to you yesterday. I am going to do it in a slightly more detail now, because quite often we come across situations where we do not want to dilute a sample to within 0.2 to 0.8 absorbance. Sometimes we do the concentration of the substance is so less that it may not be worth concentrating it between 0.2 and 0.8 absorbance, which is the normal absorbance level for all spectrophotometric methods. So, I can cite you an example of gold. Yesterday I did that. In gold analysis, people do not want to dilute and waste. So, if the color is very high, we know that according to relative concentration error system, error principle, the error also will be more. So, what can I do if I want to determine a highly colored substance? Same thing is true in case of body fluids. In body fluids, what happens? We normally have a system where the sample may be very less. Suppose somebody wants to analyze sodium in a brain fluid or in the lead in kidneys. It becomes very difficult because you can't have too much of the sample. A very small quantity of the sample will be there, and if I take that, do some pre-treatment and then do the analysis, the absorbance value will be very low. So, again the error will be very high at low concentration also. This we have studied when we studied the Beer-Lambert's law. So, to attend to such situations, a simple colorimeter which does not have the prisms, gratings and high end computer etc. are still not required. We can still make the analysis in a better way. So, what do we do? The analog scale in the spectrophotometer, we know that if we choose absorbance, it varies from 0 to 2, that is the minimum is 0, maximum is 2. If I do the transmittance, the same scale should be calibrated from 100 to 0. So, 0 transmittance corresponds to maximum absorbance. So, it will be important for us. So, the analog scale varies from 0 to 100% absorbance, that is 2 absorbance in absolute scale. So, the latter is an artificial requirement. So, when reference solution transmits more radiant energy than another standard, then scale expansion techniques can be used. I had stopped here in the last class. There are 3 ways of dealing with this. One is high absorbance method, another is trace analysis method, and third is maximum precision method. So, let us see what it entails. Look at it now. I have drawn a simple scale, analog scale of a colorimeter. You can see here that the scale I have put 4 cases here, 3 cases, and the top 1, 2, 3 and 4 are there. So, what is happening in this case is the ordinary method has a scale of 0 to 100 on the top. Okay. So, I need to analyze a sample which is giving me an absorbance between 20 to 30%. So, blank is always around 100% reference, and the sample is somewhere between 20 and 40% of transmittance. So, what I do here? So, here if the sample is having very low, what I do is I take I want to limit my range to 20 to 40% or maybe 35%. So, because my sample maximum contains 35% transmittance. So, what I do is I increase the decrease the light, so that absorbance is maximum around 2. 35% is adjusted mechanically to a value of 2, and that comes the remaining 20% will be also be expanded by the same method, but it will be somewhere between 50 to 60, and any sample in between these two would be between 20 and 35 would be measuring between 0.2 and 0.8 absorbance, and it will be showing me a better accuracy. So, this is known as high absorbance method. Another method is, suppose my sample is very dilute sample. So, what I do is, suppose it is about 80% transmittance and my sample is somewhere here, blank is somewhere here, I adjust the 100% and this 20% and 30% I adjust it to 0 level. So, any sample in between these two standards will, the scale is expanded from here to here, that is 0 to I will say about 35%. So, this is known as trace analysis method, because the sample is highly transparent here, and the error if I measure without any adjustment, it will be very high. So, I am expanding the scale from here to here between, let us say between 90, 80, 70, 75% to 0% transmittance. So, this is another way of dealing with substances which are very valuable, very small quantity of the substance available, and transmittance is very low. Now, there may be some substances where I have to adjust, it is neither at high absorbance nor at low absorbance, and then what but I need the very high accuracy. So, what I do is I select this 30% as 0% by mechanical means, by allowing more light, and 40 I adjust it to 100. Anywhere in between can be more accurately described, where the concentration can be increased and analyzed properly. So, this is known as maximum precision method. So, there are 3 systems, even though I have put 4, the maximum system is, you can choose either this or this or this depending upon the maximum precision required for the analysis. So, now we go to another utility of a spectrophotometer. Now, what I need is, suppose I have a absorbance spectrum, something like this. This is absorbance, this is concentration. So, if I plot this, normally we expect a peak with a lambda max something like this. Okay, then it is very easy for us to find out this is wavelength. So, I know where to take the measurement, where the absorbance response is optimum. Now, suppose sometimes the color is not very well defined. This is when the color is defined well. That means lambda max is precise. Now suppose the figure is something like this. You do not know whether to choose this peak or this peak or this peak, and whether the difference between this and this, could it be an instrument noise? We do not know. So, in such cases the spectrum is so vague that it is very difficult for us to decide where is the lambda max. Difficult to determine the lambda max. So, what to do now? Answer is go for derivative spectrum. So, what happens? In derivative spectroscopy, we record the spectrophotometric data and scan it, and then we plot the spectrum first. Then we can plot the first order or higher order derivative of the absorbance with respect to wavelength as a function of wavelength. That means dA by d absorbance, dA by d lambda. So, if we plot dA by d lambda versus d lambda, let us see what happens. In a derivative spectrum, the ability to detect and measure minor spectral features is considerably enhanced. See, the enhanced spectral features can distinguish between very similar spectra and follow subtle changes in a spectrum. It is also useful for the simultaneous determination of two or more components if the lambda max are very near. Now, absorption spectra of the analyte can be extracted also from turbid solutions. This is also another very important advantage when we want to do a derivative spectroscopy. So, partially overlapping peaks also can be resolved very well by using derivative spectroscopy. I am going to show you a derivative spectrum shortly. But before that, let us see some examples. What is happening? We want to determine trace amounts of manganese and zinc in mixtures by complexation with 5,8-dihydroxy-1,4-naphthoquinone. This is a organic chelating reagent. It reacts with manganese and zinc to give you colored substances. Second example is tryptophan, tyrosine and phenylalanine. These are the amino acids. They contain aromatic side chains with lambda max between 240 and 300 nanometers. I have explained to you earlier, whenever we were doing this chemical UV spectrophotometry, that in benzene ring aromatic systems the peaks are not very sharp. So, the sharp peaks are not apparent in the spectra of typical protein preparations, but they are also observed in observed very clearly in first and second derivative spectra. Then in pharmaceutical applications, definitely there will be the very good utility of such substances. So, here I am showing you the absorbance spectrum. The first one is bottom one. Look here, I have a peak which is very vague, and it looks as if it has only one lambda max and the curve is not very well characterized, that is A. Now, look at dA by lambda, absorbance first derivative, the same peak, how it is showing 1, 2, 3, 4, 5 and then one trough here and then lambda max extra. So, suppose I do second time dA square by d lambda square, then what happens? I see the lambda max should be negative, the same peaks get converted into negative peaks, but much more sharper 1, 2, 3, 4, 5, 6, so many other things. So, this is how the utility of derivative spectra can be employed to exactly assess where are the lambda max for different colored systems. So, we will also discuss about photometric titrations.